title on the safety and efficiency of virtual firewall elasticity control. And Honda Lee is going to be presenting. So let's wait for the speaker to set up.
Good afternoon, everyone. And thank you for the introduction. Okay. Here is the outline of my presentation. And I will first introduce the motivation and challenges of our work. And then I will give an overview of the Virtual Firewall Controller, followed by the more details of our approach to address the challenges. And finally, I will discuss the implementation and evaluation of our system. Firewall is a widely deployed network function that can protect networks against the malicious traffic. But traditional hardware-based firewalls is deployed on fixed locations and has constant capacity. So it's hard to use traditional hardware-based firewall to protect the emergent virtualized environments. Because in the virtualized environments, services can be migrated between data centers, and the virtual network zones have blurred and fluid parameters. So in this case, we don't have a fixed location to place a firewall. Another problem is that it's hard to decide the capacity of a firewall. For example, this figure shows a significant traffic volume variation in a DDoS attack. If we want to fully protect our networks, an expensive option is to let the capacity greater than the peak traffic load. And recently, there are two emergent network paradigms. One technology is network function virtualization. It can implement middlebox as software instances that can be created and destroyed dynamically. And another technology is software-defined networking. It provides dynamic traffic steering. NFV and SDN push forward a new type of firewalls we call virtual firewall, which is flexible and elastic to protect the networks. Virtual firewall can enable firewall as a service because it has already been included in many commercial virtualized environments. And virtual firewall can also be used to protect the traditional network. One important feature of virtual firewall is that it can scale dynamically. When a virtual firewall instance is overloaded, a new instance can be created, and partial of the traffic can deliver to the new instance. When a virtual firewall instances are underloaded, some instances can be disjoined. In order to fully utilize the virtual firewall benefits, the scaling of virtual firewall must be safe, efficient, and optimal. To achieve these features, we have some challenges should be addressed. When scaling a virtual firewall, we have two options to migrate the firewall policy. One option is that we can create a new instance and copy the entire firewall policy to the new instance. Another option is that we can split the firewall policy and migrate partial policy to the new instance. We did experiments based on real traffic data from different sources. And our study showed that the performance of virtual firewall drops dramatically as the rule size increases. So we prefer to split firewall policy for virtual firewall scaling. However, when we split firewall policy, we should be very careful to keep the semantic consistency. For example, two file rules are dependent, and this traffic should originally be denied by the virtual firewall. if we split the firewall policy and migrate one of the firewall rule to a new instance and redirect the traffic to a new instance, then the new instance will allow this flow to pass. This may cause a safety problem. Another challenge during virtual file scaling is to correct flow update. If we start a new instance and migrate partial firewall policy to the new instance, we cannot simply update the flow rules to redirect the traffic. In this example, if we simply update the action of the flow rules to redirect the traffic, some flows may be incorrectly delivered to the new instance because the firewall rules and the flow rules are not exactly matched. The third challenge is to avoid buffer overflow during virtual firewall scaling. For example, we are going to migrate a set of rules and states to a new instance. After the rules and states have been moved, some corresponding traffic may still on its way to the old instance. We call this in-flight traffic. This amount of traffic should be buffered and delivered to the new instance as well. But if we don't have enough buffer, it may cause packet loss. So we need to design the proper buffer size to avoid packet loss. Next challenge is optimal scaling. The goals of optimal scaling are to use the least number of new instances when scaling out and to merge the most number of instances when scaling in. But it's not easy to achieve these goals, considering the constraints, including satisfying service level agreements, minimize the updating costs, and avoiding buffer overflow. In this work, we propose a virtual file controller to enable the safety and efficiency virtual file control. I will give an overview here of the virtual file controller. The condition detection components in the virtual file controller can be used to monitor the status of virtual firewall instances. The dependency analysis components we designed can be used to ensure the semantic consistency during the migration. And we use the flow update analysis to achieve the correct flow update, and the buffer cost analysis to avoid buffer overflow. And we leverage the optimal scaling calculation to solve the optimum scaling problem. Finally, the migration and update control and provision control is used to guide the virtual firewall instances to make scaling. To analyze the dependencies, we define the packet space as a 5-tuple. For example, we have two rules, R1 and R2. Their packet spaces are overlapping. Then we define the relations between R1 and R2 as direct dependency. Suppose we have another rule, R3. R3 is overlapping with R2, but it's not overlapping with R1. Then we define the relations between R3 and R1 as indirect dependency. We classify direct dependency and indirect dependency as the intro dependency. Intro dependency exists inside of firewall policy or flow policy. Next, we identify the relation between firewall policy and flow policy. We group interdependent rules together. Then there are 4 relations between a firewall rule group V and a flow rule group F based on their packet spaces. They are congruent, superspace, subspace, and intersection. And we classify these 4 relations as interdependency. We identified 2 reasons that can cause the semantic inconsistency. In the first case, file rules in the same group are split across multiple instances. In this case, group is broken. In another case, the order of the file the order of the file rules in the same group is changed during multiple runs of split and merge. So the order is not preserved. To keep the semantic consistency, we propose to migrate the firewall rules based on group. Now I will discuss how to correctly update the flow rules. Suppose V is a file rule group to be migrated, and F is a flow rule group interdependent with B. If the relations between V and F is congruence or superset, we just need to change the forwarding action of every flow rule in F. If the relation between them is subspace or intersection, then change or insert is required. In this case, we will compare all the file rule VI and flow rule FJ in the two groups. If the packet spaces of VI and FJ is not overlapping, then no update is required. If VI and FJ is congruent, or the VI is a superset of FJ, then we just need to change the forwarding action of FJ. If VI is a subset of FJ, or VI and FJ are partial intersected with each other, then we need to insert a new flow rule just in front of FJ. For buffer cost analysis, we model the migration as 5 steps. Based on the model, we estimate the time for each step, and the total time of the migration was affected by the delay, transmission delay, and the bandwidth of the network, and the number of rules to be migrated. According to these parameters, we can compute the buffer cost lower bound by this formula. And for optimal scaling calculation, let X be a set of indicators indicating whether a split or merge will happen. So we can formalize the goals of scaling out and scaling in by using the indicators. We also use the indicators to formalize the constraints. And then we utilize integer linear programming to find an optimal solution for the formulas. We have implemented the Virtual Firewall Controller based on Zen and Virtual Firewall instances in ClickOS. And we have implemented our Virtual Firewall Controller on Cloud Lab, and the experiment profile is available through this link. Okay. In the evaluation, we first studied 8 real-world firewall policies. We found that the largest group size is 18, when the policy size is more than 900. That means, based on our dependency analysis, huge group is not common in practice. And we also evaluate how quickly the virtual firewall can scale. We tested both TCP and UDP flows and observed how the throughput changes. We installed 400 file rules in our experiments. And we have observed that the scaling procedure lasted a very short period of time. And in the experiments, actually, it's less than 1 second. In addition, we evaluate the impact of migration. Ideally, a migration should be transparent to the network. We reviewed how much the migration of virtual file instance affects the network throughput. We gradually increased the number of flows affected by the migration. We tested 200, 600, and 1,200 flow rules. And we observed a throughput degradation on both TCP and UDP flows, but throughput recovers quickly from the degradation after the scaling. And for the performance optimum scaling calculation, we tested up to 1,000 firewall groups to split into 6 additional virtual firewall in the scaling out case. And our calculation completes in just 0.1 second. And in the scaling case, we tested up to 100 underloaded virtual file instance. And the algorithm can complete in no more than 80 milliseconds. And in conclusion, we identified the challenges to build a virtual firewall. And in our work, we proposed the Virtual Controller to address the challenges and to achieve safety and efficiency virtual file control. And we also implement the Virtual Controller in a real NFV platform and extensively evaluate our system. That's all. Yeah, thank you. I would like to answer any questions.
Do we have any questions?